Hello everyone, welcome to this simulation, and in this tutorial we are going to understand how to produce hydrogen. There is many processes to produce the hydrogen, and in the simulation we are going to use Steam Methane Reforming, and which involves two main reactions: Steam Methane Reforming and water gas shift reactions. So during the simulation we are going to understand the kinetic of the reaction, which is important section. And we are going to use spacious model transport, and also we are going to build boundary conditions, and also during the simulation we just gonna use just one reactor, I mean just one pipe of the main processes, and the simulation has been done through this model. And without any wasting time, let's start the simulation. Well, to draw our geometry, we can use two different approach. First approach is to using a circle and giving the specific diameter and then extrude it. And the second approach is to using primitives. Well, to build geometry, we need to build a pipe. And the length of the pipe will be 1.25 meters, and the diameter will be 0.005 meter. And we are gonna establish catalytic bed inside the pipe, and which is the same with the diameter, and the length will be 0.7. So let's start with the geometry. So I will use primitives. Let's start with using that. First, we need to select our units. Our units will be meter, and I will sketch on XY plane. And use create, then primitives, then cylinder. Well, the height of the Z component will be 1.25, and the radius will be 0.025. Then generate. So this is the main body of the tubular reactor, and now what's necessary to do is to draw the catalytic bed. For that, again, we need to use primitives, then cylinder. Well, the origin Z coordinate will be 0.2, and the axis for the Z component will be 0.75, and the diameter is the same. Then generate. And pay attention, the operation will be add material, will be add frozen, and then generate. Yes. As you see here, our catalytic bed has been appeared. So this is our catalytic bed. And the more important thing is that first cylinder will be add material, and the second cylinder as a catalytic bed should be selected on add frozen. So what's the next is to define name selection. Yes, name selection. Here is inlet, generate. Here is outlet. generate. Here is, we use phase selection and not the volume selection. And for the reactor wall, because we need to adjust the temperature and to see the temperature distribution along the pipe walls, we need to use the phase selection. So for the first reactor, as you see, wall. Then click on generate. And the second will be volume of the catalyst. I used volume selection. Name selection then. Cat volume. Then click on generate. So our geometry has been created properly. The methane and steam will be entered from the inlet, and they are going to get in touch, and they are going to contact with the catalytic bed. And from the outlet, hydrogen is going to go outside. Well, our geometry is completed, and next is to create our mesh. Now, after the building of our geometry, we need to establish the meshing part, which is a quite important section in order to have a good convergence and avoid instability. Well, during the simulation, we are going to use multizone and mesh, and we are going to using H size and some different methods. So let's start with the meshing. Well, now let me walk you through the meshing processes, which is one of the most critical steps in setting up a reliable CFD simulation. The geometry of a reactor is relatively simple in the shape, but because it involves the complex transport and chemical reactions, and the quality and resolution of the mesh must be handled carefully. So, as you see, this is our pipe, and I start by defining a global element size of 0.004 meters. This value was chosen after considering the reactor's diameter, the expected velocity and temperature gradients, and the need to resolve the detailed reaction zones. Well, smaller element size allows for better spatial resolution of gradients in the species concentration and temperature, especially near the walls and the catalytic bed, which is where the most of the chemical activities occurs. Well, as I said, the element size will be 0.004, and the sizing, yes, the maximum size is 0.008, and they are almost good, and then generate. Well, our mesh has been created. As you see here, pay attention to this criteria. It's quite important. Maximum aspect ratio, minimum element quality, minimum orthogonal quality, and maximum stoicness. What's necessary to do is that using phase meshing, or also to build mesh, the kind of the mesh. I will use the multizone meshing method. Well, method, and I'm gonna select it all the geometry and then click on apply. Then the method will be multizone. Then click on generate. Well, this method is ideal for geometries like tubular reactors, where a structured mesh is preferred in the cylindrical regions for better alignment with the flow. Well, the multizone approach allows to divide the reactor into hexahedral and prismatic blocks, ensuring high quality elements in the axial and radial directions. This significantly improves the solver performance, especially for problems involving reactor flows and heat transfer. Well, the next is to further refine the mesh and control the resolution along the length of the reactor. And I'm gonna apply phase meshing. This was done to ensure that the flow leaves the domain through a clean structure mesh. This helps to prevent artificial backflows and improves the convergence stability. And I'm gonna using a facing mesh, and I'm gonna select this and then click on apply. And everything is good, and then click on generate. And as I said, this improves the convergence stability and reduces the numerical diffusion. Since the outlet is where we evaluated the product distribution, especially the hydrogen yield, ensuring a good mesh here directly impacts the accuracy of our final results. Well, as you see, this has been done. And what's the next? To further refine the mesh and control the resolution along the length of the reactor, I'm going to apply the edge sizing using a division. And I'm going to use the sizing and choose this edge size, and geometrically can apply, and the type will be number of division will be 70. Then click on generate. Well, this gave more control over how many elements were generated along the specific directions, particularly along the axial link where the flow progresses and the reaction evolve. More division mean more data points to results how species like methane and hydrogen change over the reactor length, which is critical for capturing the chemistry accurately. And as you see, and I'm gonna add another sizing for each size here, and click on apply. Then number of division will be 75. Then click on generate. It's good. And also, what's the next? We will gonna hide the solid body. It's the reactor body. And we are gonna adjust the catalytic bed mesh to have a good control. Then sizing, and the same approach will be applied. Then click on apply. number of division, and 80. Then click on generate. Yes, as you see, the maximum aspect ratio has been decreased here. So we need to decrease this value to acceptable limitation. And then for inlet, we will use sizing and the same approach. Click on apply, number of division, it will be 19. Then click on generate. It's a good. And I'm gonna use a face meshing here also, and then click on apply and generate. Well, this is the mesh has been created, and I used edge sizing as you see here, and face meshing and multi-zone, and I need to suppress and show body. Okay, and this is overall shape of our meshing. As you see, it's quite good, and you need to control. As I said, maximum aspect ratio is 4.97, and this is 0.27, and you should pay attention and be careful about this number and the limitation, and to check it again. And if you want to use this numbers to your simulation, pay attention to the numbers, and the quality smoothing is medium, and the inflation is 0.27, and maximum layers 5, grow rate 1.2. And I've used the multi-zoom method as you saw, and face meshing and edge sizing, and this mesh has been created. Well, overall, this meshing strategy was not random. Well, every steps from choose of the element size, the use of a multi-zoom meshing, edge sizing along the length, and the face meshing at the outlet was chosen to enhance the both physical accuracy and the numerical robustness of the simulation. It allowed me to confidently simulate the highly sensitive reaction environment inside the reactor without introducing artificial errors from poor mesh quality or resolution. This is the catalytic bed mesh part, and the final mesh consisted of the structure elements through the most of the domain with the smooth transition and the minimalist weakness. This gives a solid foundation for the accurate prediction of the species transfer, reaction progressions, and the thermal behavior. All of each are essential to understanding and optimizing hydrogen production and the reforming processes. So the meshing part has been finished, and this is, as you see, this is our pipe. And after the meshing, we will gonna discuss about setup, how to make a setup, how to define reactions. Follow me and follow the tutorial and to see how the reaction, how boundary condition, and how other parameters, criteria are going to use in this. Well, here is the final part, and includes setup and post-processing. In the setup part, we are gonna use different models like species transfer model and radiation models, and we are gonna define our reaction and also kinetics, and then we will use the boundary condition, inlet and outlet, and we are gonna further adjustment at the cell zone condition. We are gonna give the details for catalytic bed. So after that, we are gonna using the solvers, and we will initialize then run it. So for the post-processing, we will see about the hydrogen yield and the conversion of the methane along the reactor, and also we will see that temperature distribution along the reactor, how it affects on the yield and the conversion of the methane. Let's to see the simulation. Well, once the meshing processes was complete, I moved on the setup stage, where the physical models, boundary conditions, and the material properties was defined. This stage was essential to ensure that the numerical model truly reflected the real-world behavior of the steam methane reforming processes. So as you see, this is our pipe, and the mesh has been done. I can show you the edges and the nodes, especially the edges. As you see, this is our mesh, and you can see another options. Well, I begin by selecting a pressure-based steady state solver, which is appropriate for this kind of the law of split reacting flow. Since the reforming processes involve a strong temperature gradient and the chemical heat effects, I enable the energy equation. I've done it, and to capture the full thermal behavior given the high temperature nature of the reactor. And I also activated the radiation model using discrete oriented DO, and to model account the radiative heat transfer. And this part is a quite important section, species transport. Before starting the species transport, we need to define our material. Like starting here, and from the material, all the material exists inside the Fluent database. If it doesn't exist, you can use properties of that component. If it is in the vapor phase, in the liquid phase, or in the solid phase, you can enter the properties here. And or if not, if it is inside the Fluent database, you can easily choose your component. For our reaction, we need to have a water vapor and also hydrogen. It's here. Hydrogen and methane, or let me to find a carbon monoxide and carbon dioxide, as well as, and also methane. When you choose your specific component, you just need to click on the copy. And I've copied before, and I'm not gonna add it again. And you can easily choose your component from this section. And what's after the selection of your component as a fluid, I've selected carbon dioxide, carbon monoxide, hydrogen, methane, nitrogen and oxygen. We don't need this. And after the selection, we are going to go through the species transport reaction. For the species transport, I use the species transport model with the finite rate, or you can use this eddy dissipation, and you should turn on the volumetric reaction, and this allows to define the ether reaction kinetics for the both steam methane reforming and the water gas shift reaction. Well, after that, you need to create a mixture template, and when you created your mixture template, at the material section, the mixture will be appeared, and you will see your mixture template. And if you want, you can change that name. And from the mixture species, you will add all component that you need in your simulation. I added water vapor, methane in the gas phase, and the hydrogen, carbon monoxide, and the carbon dioxide. So this also we need to write our reaction, and for that reason I will start with the edit and the reaction. So we have water steam methane reforming reaction and the water gas shift reaction. I defined the chemical kinetics as a volumetric reaction, meaning that the reaction occurred through the catalyst filled zones as a bulk reaction process, and not just at the surface. This is a process appropriate for the porous catalyst, where the gas phase reaction occur within the volume of the catalytic material, and not only on its external surface. It allows us to model the effect of the catalyst distribution across the finite region and capture the spatial evolution of the species and the heat within the catalytic bed. Well, there are the key reactions involved. The first is the steam methane reforming SMR reaction, which is a highly endothermic, and the species is methane and water vapor, and pay attention to stoichiometric coefficient is 1 and 1, and the product is carbon monoxide and the hydrogen. The coefficient is 1 and the coefficient for hydrogen is 3. This reaction drives the hydrogen production and requires a significant heat input, which is why the inlet temperature was set high. And I'm gonna show that. And pay attention to Arrhenius rate. And this value should be used. And because the reaction is reversible reaction and not irreversible, so the conversion playing important role because all the reactant doesn't consume inside the reaction, so the product has been created. The product has been created then by the backward reaction. You need to specify that this value create a small amount of reactants, for the backward. For the second one, the total number of the reactions should be 2, and for the second reaction, as you see, it's the water-gas shift reaction. This reaction is slightly exothermic and helps to convert carbon monoxide to additional hydrogen. And as you see, the stoichiometric coefficient is 1, and for reactants and for the product. And pay attention for activation energy, and it's include the backward reaction also, and pre-expressional factor and activation energy for the water-gas shift reaction. For each reaction, I use as you see, Arrhenius formulation to define the reaction rate. This means that the reaction rates are dependent on the temperature and the concentration. Also, this reaction depends on the partial pressure and of the reactants. I inputted the pre-expressional factor A and the activation energy and the temperature exponent, all of which were derived from the validated kinetic data. Since the reactions are reversible, as I said, I also included the backward reactions, either by specifying reverse Arrhenius parameter or using the Fluent, building the thermodynamic equilibrium relations, which allowed the software to compute the reverse rate based on the forward rate and the equilibrium constant. As I shown that the reaction rates also depends on the local temperature and species mole fraction, making them sensitive to thermal and mass transport behavior within the reactor. This was about our reaction part. As you see, this set off with the multiple Arrhenius-based volumetric reaction occur in the specified catalyst zone allowed for us to simulate the real catalytic reforming behavior. It gave the detailed view of how methane gets consumed and how carbon monoxide transferred and how hydrogen accumulates along the reactor link, and all under the influence of the heat reaction kinetics. Then click on OK. After adjusting and giving data of your kinetic, pay attention to these properties of the mixture. And density, you can use this. I've used with the ideal gas and the specific heat. I've used the mixing law for thermal conductivity. I've used the mass weighted mixing law. And for viscosity, I've used mass weighted mixing law. And for the rest, these numbers. And click on change or close. I don't make adjustment, and I can click on close. Well, what's the next step is to adjust our boundary condition. For the boundary condition, I will start with the velocity magnitude. If you want, you can use mass flow. You just come here and you just select your inlet, and you can just select your type. Velocity inlet, pressure outlet, and interface mass flow inlet. I was discussing about this. You can add the mass flow inlet, or if you don't want to use the mass flow inlet, you have area of your inlet, and you can find your area and then try to find the velocity inlet. And I'm just using the velocity inlet. And I've chosen the velocity magnitude 0.70 and gauge pressure with this number, and also thermal condition of our mixture, which is going to come inside the reactor. I mean methane and steam with that temperature, and the radiation will be this, and the species mole fraction. Well, the amount of steam and methane is quite important because steam and methane division should be around well, it should be around 3 or 3 or 2. Well, I've chosen 0.74 for steam, and for methane 0.25, and for hydrogen and carbon monoxide I've used this number. I can use 0, but for stability of my system I used a small amount of hydrogen and carbon monoxide. Then click on apply, close. Well, the outlet was set as the pressure outlet with the gauge pressure, allowing flow to leave and track with the pressure. Well, for the outlet, I've used the gauge pressure with the 5 bar almost, and pay attention to the units. Here is the Pascal. And for the thermal condition for the backflow, I've used this number, and it depends on you. It should be a little bit higher than the inlet temperature. to have a good stability of our convergence and our radiation in the species. So I define that this amount of species going to have a backflow doesn't affect, but you need to enter a value for the backflow condition to be recognized to the systems. If the backflow exists, this number should be used. Then close. Then reactor wall. And the reactor wall where for the wall I've used temperature. I've selected the temperature, and also you can select the radiation also, and you will gonna give the thickness. I'm using a simple one, temperature, and the temperature for the reactor wall. If you remember from the geometry part, I have selected the reactor wall, and then now here I'm gonna enter this value 1100, and the thickness of the wall will be this. Then click on apply, and for catalyst wall or cat volume, I'm gonna use this number. Then click. Well, another important thing is to enter the porosity of the catalyst, cell zone condition, fluid, and cat volume. Oh, here is an important section, and you need to define your porosity. You select this pros zone and pros. The zone will be appeared, and the porosity will be 0.4. And if you want, you can use this options, also the reactions and surface to volume ratio. What's the surface to volume ratio? Well, the surface to volume ratio is a crucial parameter in the reactor design and analysis, especially in the catalytic and the heat transfer systems. Well, in the catalytic reactor, like the tubular reactor, the catalytic surface area is where the actual chemical reaction occurs, while the volume refers to the space the gases occupy as they flow through. The surface to volume ratio essentially indicates how much catalytic surface is available for reaction per unit of reactor volume. Well, a high surface to volume ratio means more surface area is available for the reactants to interact with the catalyst, leading to faster reaction rates and a better conversion. Assuming that the reaction are the surface limited, and macro reactors or packed bed reactors with the small diameter pellets or monoliths, maximizing the surface to volume ratio is often key design objective to increase efficiency and your system. I think this explanation it's enough to understand what's the surface to volume ratio, and we can proceed with our setup. Then click on apply. And what's the next is to use a monitor and the residual. Our residual should be in this limitation, and then click on apply. And for seeing that have hydrogen getting to steady state, you can easily select reports plots, and from new, and you can create the new and surface report, and an area weighted average. And from the outlet, I just want to see the amount of hydrogen in the outlet. I will use the species, then mole fraction of hydrogen, and you can easily select hydrogen, and you will see the distribution and the yield of and the conversion of your methane also. I've created before, and like the velocity, temperature distribution, and for the temperature distribution you should come and use surface area, and from where you want to see your temperature distribution, I've selected the plane, and from the temperature I'm gonna see the temperature distribution along the reactor, and then click on apply. Okay. And what's the next? And how to create the surface. I've discussed about the creation of the surface at the previous videos, and you can simply use the surface plane. From which plane you just want to discuss, from the YZ plane or ZX plane or XY plane. I'm just gonna discuss about the YZ plane. You just create your plane, and when it's created, when it has been created, you will just see your report option, and you can use easily. And what's the next? We need to see our methods, the solver and solution methods. For the pressure-based velocity coupling, I used simple, and the gradient and pressure density and momentum was quick, and I used the higher order term relaxation factor. And then when we just easily start with the initialization, the gauge pressure is this one, to leave the gas betterly from the outside, and the Z component is velocity of the inlet, and I've used this number. Otherwise, you can easily use the hybrid initialization. I just want to enter the manually for my initial condition for the initial values. And then you will run the calculation, and after running the calculation, you will see that your component reached the steady state condition. All of this is good and continue to reach to 10 power minus 8 and other criteria also. That was okay. And what's the next? Let's start with the area weighted average of the mole of the hydrogen along the reactor. After this iteration, this reached the steady state condition, and to a value of, as you see, 0.53. And after this, doesn't change the value of the hydrogen. And this is our steady state condition. And let me to show you better visualization about the hydrogen production. And I'm gonna select the species and the mole fraction of the hydrogen on the plane 4, then display. Yes, this is the hydrogen production along the reactor. Well, in this visualization, we can see the contour of the mole fraction of the hydrogen along the axial length of the reactor. Hydrogen generation begins as a steam methane reforming reaction initiates, and it increases progressively through the catalytic zone. The concentration rises gradually, reflecting the conversion of the methane and the steam into carbon monoxide and hydrogen, then further into the carbon dioxide and more hydrogen via the shift reaction. Well, as you see here, the highest mole fraction of the hydrogen is achieved closer to the end. This is the inlet, and it's blue. As you see, we haven't any hydrogen, and this is the outlet. We have the hydrogen with the contour reaching a peak value about 0.57, and this validates that the reaction is taking place efficiently, and through the some optimization may still be necessary. And this distribution clearly shows the effectiveness of the catalysts and the thermal gradient and prompting the reaction. And factors such as surface to volume ratio, reactor temperature distribution, and pressure significantly impact the yield. And current surface to volume provides an adequate catalytic surface area to support the reaction, but enhancing it further may improve the conversion. And similarly, optimizing the inlet molar fraction, flow rates, and activation energy constants in the Arrhenius equation can be both hydrogen input. And if you do that, you will see a higher amount of hydrogen has been created at the outlet. Well, let me to discuss about temperature distribution also. and display. Well, yes, this is the temperature distribution. As we move downstream towards the outlet, the temperature, as you see here, it's a bit increasing, and from the inlet we have the low temperature, and then it's increasing gradually. So the temperature is quite important. This thermal distribution also affects the selectivity and conversions in your reactor, and the initial high temperature also helps to achieve the rapid methane conversion, while the gradual cooling is the water-gas shift reaction, which is the favorite at the low temperatures. Therefore, this distribution, while not uniform, may support a two-stage strategy: high temperature for reforming, a low temperature for the maximum the hydrogen via the shift reaction. I'm gonna show you methane, moles of the methane along the reactor. And as you see, it's started here, and then it's gradually decreased, and it reached to this value at the steady state condition. And this is the velocity magnitude, and as you see how the velocity change along the reactor. And this is as you see, this is the temperature distribution along our reactor. And I think it's enough. And another thing to say that for this simulation, you can use user-defined function. You can define your kinetic reaction by the UDF. If you want to use the partial pressure of each component for kinetic rate, you can write it in C+, and then you can easily add your UDF with the C+ template from the user-defined function section and the function, then manage, and try to load your UDF here. And I'm not gonna do this, and maybe for the further simulation we can work with the UDF to see how UDF works, and how it merge with the momentum, with the continuity, with the volume fraction of each component, and where should to added these UDFs also. The mostly we can add it in the cell zone condition. Let me to show you a bit. For the cell zone condition, if you want, you can use your source term. If you use this option, the source term will be activated, and you can easily change your component, or give your specific condition for your component, like the mass or momentum or turbulent kinetic and other. And you can add from this, and you can, if you added UDF before, you will see your UDF at this section. And until here, it's enough. I hope this simulation will be effective. And have a good optimization, you need to adjust your inlet condition and especially your velocity inlet to increase or decrease your residence time, because it's quite important also. And I think it's enough. It's the I think from here it's enough, and it's the end of the simulation. And I hope see you soon at the other simulations. And don't forget to like and subscribe to support the channel. Thank you for your attention.